Good morning. Okay, good morning once again. So we're studying Fourier series. Now last week we did a fairly patient setup of it, or motivation, and I motivated the concept of a Fourier series by connecting back to concepts that you're familiar with from your initial study into linear algebra and vector spaces. Okay? And that led us to, so I'm not going to repeat that setup. If you weren't here, please do have a look at the recording of the last lecture. But a Fourier series is this kind of expression in equation 3.1 there. Equation 3.1, first page of chapter 3. And it's a way of taking suitable functions f and re-expressing, finding a certain kind of standard representation for the functions. The standard representation is as a linear combination of sine functions and cosine functions. Now it's an infinite linear combination, and there also appears a constant term in the representation as well. We indicated that the kind of setting for this can be given an interpretation in linear algebra, as we're going to be looking at a vector space of suitable functions f. And these are expressions as looking at a typical vector in the space and expressing it as a linear combination of the basis vectors. Okay? So up here we have these basis functions, the sine functions, the cosine functions, and the constant function. And this theorem, this first theorem that we're looking at, okay, we're not going to give a very detailed proof of it. We'll give some arguments in support of it today. But it asserts that we can do this. Okay? Whenever the function f is reasonably well behaved. And we're looking at a function, we're studying it on an interval from minus pi to pi. Pi is chosen because it matches the typical periods of the cosine function and sine function. Okay. And as long as our function f has these nice properties, which are quite permissive, the function is allowed to be discontinuous. So it can have discontinuous jumps, the function f, inside the interval minus pi to pi. But it cannot be too pathological, cannot have an infinite number of discontinuity. But it's allowed to have any finite number of points of discontinuity. Secondly, it's allowed to have as many turning points as it wants, just as long as that number is finite. Okay? Again, it'd be quite the pathological function to have an infinite number of turning points inside this finite bounded in this interval of finite length from minus pi to pi. So providing our f is like that, it's a nice continuous function, not too many discontinuities, not too many turning points, then this theorem asserts that it has a Fourier series. And that equality holds between this infinite series and the function at all points except at the points of discontinuity. At the points of discontinuity, something funny is going on. Now, what are these expressions here? fxd plus and fxd minus. Those are simply the left-handed and right-handed limits as you approach the point of discontinuity. So it looks complicated on the page there, but it's not that bad in real life. You just imagine, okay, I know some of you are far away because you've chosen to sit at the back, but there's not too much detail in this picture. So here's a clear point of discontinuity of the function, okay? This point here. xd is a point of discontinuity. The function makes a discontinuous jump in value, okay? So these two quantities, fxd plus is the limit as you approach x from above. So fxd plus will be this limit up here, and fxd minus will be this quantity down here. Okay, fxd plus and fxd minus. So the limit in values of the function as you approach xd from above is fxd plus. The limit as you approach the point of discontinuity from below is fxd minus. So now the Fourier series will be doing some kind of thing around here, Fourier series, but the theorem says that, well, these points of discontinuity are awkward. this infinite series here, this is a nice continuous function. And what it's going to do is it's actually going to give you this average value. Okay, so at the points of discontinuity themselves, the Fourier series, it's got to be equal to the function at the left and equal to the function at the right. So it has to do some kind of thing. And it'd be a bit biased if it took on either of these left-handed or right-handed limits. So the fairest thing to do is for the Fourier series to give you the average value between the two. So this midpoint in the discontinuous jump. That's the value that the infinite series will return at the points of discontinuity. Okay. So actually, strictly speaking, probably on the right-hand side here, you should have xd. So in your notes, if you stick the subscript d on those x's on the right-hand side of equation 3.2, because we're talking about evaluating the Fourier series at the point of discontinuity. So those x's there on the right-hand side of 3.2 will be xd. Okay. So that's what Fourier series are. And we're going to work our way towards, hopefully by the end of this morning, we'll have seen one or two of them calculated. Let's just look at some of the initial tasks that we're doing. So there's a first example here. And this connects with the linear algebra. So what we're saying is that this set of functions, the cosine functions, the sine functions, and the constant function, we're claiming that this is what's called an orthogonal family of functions in the vector space. Orthogonal family of functions means that if you take any two of them, they are orthogonal to one another. Now, orthogonal here means, well, in the case of simple position vectors of 2 and 3 dimensions, you're familiar with the notion of orthogonality. In the original geometric meaning, it means perpendicular. So the vectors would be perpendicular to each other. And we don't really have a geometric picture in our heads of this infinite dimensional vector space, but we still think in terms of properties that are generalizations of the notion of perpendicularness. Okay? So what it means is that if you take any two functions, so phi and psi here are a selection of a pair of functions from this family f. As long as they're different, they're going to have an inner product of 0. Okay? Perpendicular vectors meant it had a scalar product of 0. So the generalization of that is orthogonal vectors means they're orthogonal with respect to a certain inner product. The inner product we're using here is the standard inner product on the interval minus pi to pi. So you integrate the product of the functions. It's the continuous version of the scalar product, the dot product that you're used to with 2 and 3 dimensional vectors. So the claim is that this family f is orthogonal. So we take any selection of a pair of functions, phi and psi, different functions, then they've got an inner product of 0. Now, we can prove this. The details of the proof is just carrying out various integrals of sines and other sines, or cosines and other cosines, or cosines and sines. So we might look at one or two cases of that as an example here, or maybe just the one case to get you started. So switching to the document, switching to the visualizer here, we'll have a look at example 3.1. And so one part of the orthogonality would be in example 3.1. So we let phi of x is going to be one of the cosine functions, cosine mx. And psi of x is going to be one of the sine functions, sine of nx. Okay, so these are two functions from that family f. Okay, I'm not saying what m is or n is, but m and n are two integers bigger than or equal to 1. Okay. F being an orthogonal family, of functions, means that the inner product of phi with psi will be, or well, I won't say it implies that the inner product of phi with psi should be equal to 0. So let's check that. It'll be part of the proof of proving that F is an orthogonal family. So we can go for the inner product of phi with psi. By definition, the standard inner product on this integral. So we're integrating the product of the two functions. So this becomes the integral of cosine mx times sine of nx dx. Now this is an integral that we should expect to be able to explicitly evaluate. It does have some undetermined stuff in it, m and n, but maybe m and n are integers, we know. And it's on a nice interval with respect to cosine and sine, so it's going from minus pi to pi. So we should be able to make some definite progress in integrating this. Now, I don't know off the top of my head what the integral of a cosine multiplied by a sine would be. I mean, you could look them up in formula books, but generally the view taken is that if you want to do this integral by hand, you want to take this product of cosine and sine and turn it into some equivalent expression involving as a linear combination of either cosines, individual cosines, or individual sines. And those you'll be able to integrate. So we need one of that large family of trigonometric formulae. And there is one of these for the product of a cosine and a sine. Okay. So what we'll do here is we'll make use of the general formula cosine A sine B. Turns the product of those two into a sum of certain sines. So it's sine of the sum plus sine of the difference. The sine of A plus B plus sine of B minus A, and it's a half of it. Okay. So using that, our integral, continuing the chain of equations, we apply that to our integral. Our integral is going to become a half times the integral from minus pi to pi. And we're going to have sine of m plus n x plus sine of n minus m x dx. Okay. The capital A is mx, the capital B is nx. So it's sine of the sum plus sine of the difference. Now it's reduced to something we can integrate. Yes, it's a single sign, well, it's two single sign functions, a linear combination of them. And the integral of sine is whatever it is, minus cosine. Except we got to think about the parameters m and n here. I mean, typically, yeah, the integral of these two will just be the corresponding cosine, but maybe it depends on whether n and m are the same or not. Okay? Because, well, you see, if m and n are the same, then this is actually sine of 0 times x, which is maybe significant and maybe causes us to treat the integral differently. So assuming first, the general case, assuming first that n is not the same as m, so that this difference is not 0, that it is two genuine sine functions, then it would integrate to 1/2 of, and this one would integrate to minus cosine m plus n x divided by m plus n, and this one would integrate to minus cosine n minus m times x over n minus m. And this is all to be evaluated at minus pi and pi. Okay. Okay, what's those evaluations going to be? Well, they're going to be evaluating cosine at some kind of integer multiple of pi and minus pi. Okay. But in particular, you're evaluating it once at plus pi and once at minus pi, and you're subtracting those evaluations. Okay. But remember, cosine has a very important property that cosine of minus z, calling it something different to not confuse with any of the letters in use at the moment, but cosine of minus z is always the same as cosine of z. Okay. Cosine, this is what's called an even function. You evaluate cosine at a certain argument z, it gives exactly the same value when you evaluate it at minus z. When you look to the right of the y-axis in the graph of cosine, look to the left, it's exactly symmetrical. Cosine function. It's not the same for sine. Sine takes the opposite values. Okay, but cosine is exactly symmetrical across the y-axis. So that basically means that this comes to 0. Okay, because this evaluation at x equals plus pi gets a certain value, but when you evaluate it at x equals minus pi, you're effectively evaluating cosine of minus z. So it's going to get the negative, it's going to get the same value, but then they get subtracted because it's evaluating the upper limit minus the evaluation of the lower limit. And the same for that second one. So we get 0 as expected. Yeah, we were supposed to get 0. We're trying to show that these are orthogonal vectors to one another. Now that was in most cases when n is not the same as m. And secondly, or conversely, if n equals m, so that's the other possible way the world could be, if n was equal to m, then the inner product, let's pick it up again. The inner product is just going to become a half times the integral minus pi to pi just of sine m plus nx, just this part. Because the second part, this here, you'll see this just be sine of 0 times x, and that's always going to be 0. So it's just equal to that. But again, the same thing happens. This integrates to this expression minus the cosine of m plus n times x over m plus n, evaluated at minus pi and pi, and that again is 0, as expected. Because you're just evaluating cosine at a positive argument and the same magnitude negative argument, and subtracting the values, so it's going to be 0. Now, as an exercise for you to do is to complete the proof of orthogonality. I.e., that the inner product of 1, the constant 1, with any sine function is equal to the inner product of 1 with any cosine function. That the inner product of any, well, we've done sine and cosine, so the inner product of any sine with another sine, and the inner product of any cosine with another cosine. So I've got sine nx, sine mx, cosine nx, and cosine mx, that all of these are 0 when n is not the same as m. Okay, because being an orthogonal family means that when you take an inner product of any pair of elements, vectors, functions from the family, their inner product is 0. So in the example we've just done, we've done the case of one sine function with a cosine function. So the other cases to show for the way a possible pair could be selected is the constant with one of the sines or constant with one of the cosines, or 2 different sines or 2 different cosines. Again, they're all going to be examples of integrating various combinations and products of sine and cosine. And so on. And all be tackled in the same way, or a similar way. We just tackled those arguments there. Okay. Example 3.2. Okay, so orthogonality means the inner product is 0 for a pair of different vectors. What kind of things do we get when we take the inner product of a vector with itself under this thing? Okay. So this example 3.2 just looks at one of these. If we were to take the inner product of a sine function with itself. So this is sine nx with sine of the same nx. Okay, the multiple of x is the same. So this will not give us 0. Remember, we're dealing with an inner product. And the third, when you looked at the definition of an inner product with Stephen, the third criteria for being an inner product is the positive definite criteria. But the inner product of a vector with itself only gives 0 if the vector is itself the 0 vector. Now, sine nx is certainly not the 0 function. 0 function is the constant function that's constantly 0. Sine nx is certainly not the 0 function. It occasionally takes on a single value of 0 for certain arguments, but it's not the 0 function. So what do you get here? Well, by definition, this is the integral of the square of sine nx. So if you want to evaluate that, well, you either look up a formula for the integral of the square of a sine, or you use, I mean, the general way you think about, I can't remember what the integral of the square of sine is, so I should convert it using one of the standard formulae into something, either a plain old sine or cosine that I can integrate. So the thing to use here would be the, sometimes called the square sine formula, the double angle formula. So the way you use it here is that sine squared of x is 1 minus the cosine of 2 times x. Half of 1 minus the cosine of 2 times x. This is sometimes called the double angle formula for cosine. If you reverse it, it tells you what cosine of twice an angle is. Converts it into an expression of sine of the single of half the angle. So using this here, we can convert this integral into a half times the integral minus pi to pi of 1 minus the cosine of 2nx dx. Well, that's a plain integral we can do just with standard integral of cosine. Cosine integrates to sine. And adjust using the chain rule effectively for the fact you've got a multiple of x here. And integrating constant 1 gives us x. Oh, sorry, I'm actually doing the integration here. So integrating 1 gives you x. Integrating minus cosine gives us minus the sine of 2nx divided by 2n. And that gets evaluated at x at pi and minus pi. Okay, what's this? Well, x gets evaluated at x and minus pi, or pi and minus pi, fine. Sine gets evaluated at 2n. Okay, well, 2n is an integer multiple of pi or minus pi. So it's always sine of an integer multiple of pi, which is 0. Okay, places where sine takes on the value 0 are exactly the integer multiples of pi. So this part doesn't contribute anything to the evaluation because it's always 0. And the x contributes, well, just pi minus pi. So in other words, a half 2 pi. So in other words, just nicely pi. So pi comes out as the value of the inner product of that sine function with itself. So for another further example exercise is to check the evaluations. Check the evaluations of a cosine of an inner product of one of the cosine functions with itself. And that will give you, well, it will give you pi again. It behaves similar to the sine functions. And if you take the inner product of the constant function 1 with itself, well, this is slightly different. You actually get the value 2 pi. The fact that this comes out as 2 pi, that explains why in the expression of the Fourier series, the constant coefficient is expressed as a half of a parameter a0, rather than just, say, an a0 itself. There's this extra factor of 2, or equivalently factor of a half, floating around the picture. So our decision to take the constant function 1 as one of the basis functions, that kind of forces us to make it all work out nicely to take the constant coefficient in the Fourier series as the parameter as expressed as half times the parameter A0. You could straighten it out and keep your constant term in the Fourier series as just the plain parameter A0 if you chose to take a modified constant function as your basic basis vector. Might be something like a half or 1/√2 or something. That would make this inner product of that function with itself come out as just pi or something. Could well be, yeah, it's probably 1/√2. But we take the view that choosing a standard basis function as the constant function 1/√2 would be a bit awkward and unsightly. It's much nicer to choose it as the constant function 1. So there's this kind of slight anomaly or wrinkle in the whole thing. There's a factor of a half that must be dealt with somewhere. But the decision has been taken traditionally to deal with it in the expression of the Fourier series itself. Okay. So we've seen examples of proving parts of the fact that it's an orthogonal family of functions and looking at what the evaluations of a function with itself comes out as. One of the basis functions with itself. So we now move on to looking at the Fourier series coefficients. So I'll just briefly switch over to the notes again, your printed notes. So we look at the next section, section 3.2. So this declares for us what the Fourier series coefficients are. How to think. Okay. And this is where we're not going to quite prove the Fourier series theorem, but we're going to give some arguments in support of it. Okay. So this is what our Fourier series is. It's this infinite combination of cosines and sines and a constant that's equal to the function f. And it's determined by these coefficients. The constant parameter A0, the coefficient of the cosines, AN, the coefficient of the sines, BN. So those are the coefficients in the linear combination. They're like the components of the vector in the infinite dimensional vector space. How do we work these out? How do we evaluate them? How do we relate them to f? They're related by these Fourier coefficient formulae. Constant parameter A0 is the integral of the function on its own, which is effectively the inner product of the function f with the constant 1. Or the rescaled inner product, the 1/pi times. The AN coefficient is the inner product of the function f with the cosine function, with the same index n, and similarly for the BN coefficients. And in example 3.3, we don't quite give a proof of this, but we give a little bit of an argument in support of it. What we're going to do here is, assuming that such a Fourier series exists, okay, assuming that some kind of expression for f as a combination of sines and cosines exists, can we prove that the coefficients must be given by those formulae? So we're not quite demonstrating the existence of these expressions for f, which the theorem asserts. But what we're doing is, well, assuming any kind of expression like this exists for f, show that it has to be with these coefficients given by these formulae up here. Okay. So that's saying if it has to be a solution, it has to be that one. Actually demonstrating that that is the solution needs a bit more detailed analytical work to demonstrate the existence of this. But we can at least give this kind of supporting argument in favor of the theorem. And it gives a bit of indication there, or does it? No, it doesn't. But you see, we've just been talking about orthogonality. So that's what we're going to exploit here in example 3.3. So example 3.3, so we assume the existence of a Fourier series for f So this is f of x is a half a naught. You don't necessarily have to write this down again, but I'll just write it down on the page so the argument is complete. So we're assuming the existence of this. N from 1 to infinity in both cases for some coefficients. The a naught, the an, and the bn. What we're going to demonstrate here is show that the coefficients have to be given by those inner product expressions that we just looked at. Okay? So then consider, for example, what happens when we take the inner product of f with one of the sine functions, sine mx. Now, yeah, so I'm indicating n as the summation index up here, n. So n is doing a job of running through all the positive integers. So I don't want to pin it down and make use of n, because n is like a summation index. So we shouldn't pin it down to a particular value. So I'm going to talk about sine of mx. So this m appearing here is some positive integer. So it's one of the values taken on by the summation index n as it goes from 1 upwards without n. Okay. So we consider that. So we think of this as the inner product, and I probably won't write it down. I won't write it down because it will distract us. So what I'm doing is I'm taking this whole infinite series expression here and imagining it there. I mean, you can write it in if you want, but imagining it here is the first argument in the inner product. We're taking the inner product with this huge beast with sine of mx. Now we're going to allow ourselves to use the properties of the inner product. Now with Stephen, you've been doing some work in proving whether or not candidate two variable functions are or are not inner products. And one of the conditions that you have to verify or prove fails is the property of the claimed inner product being linear in the first entry. Yeah. You have it, I think he expressed it as a phi of alpha u plus v broke apart as alpha times the phi of u with the other thing plus phi of v with the other thing. Okay, that's linear in the first position. Well, we take the view that our thing sitting in the first position here is just a big linear combination. So we're just going to go ahead and break it apart using the principle of linearity. Okay, so using the linearity of the inner product, this we're going to break apart as, so we're taking the inner product of everything with the sine function. So it's going to be a half of a naught times the inner product of 1 with sine of mx. Then it's going to be a big sum, and you see the sum is coming outside now. Of the inner of an times the inner product of, so this is the cosines, the cosine of nx with the sine of mx. Your n's and m's distinct. Jurisdiction is needed. Then we got the infinite sum of n from 1 to infinity of bn times sine of n, x, n for Nigel, and sine of mx, m for mother, in the second position. So, okay, what happened there again? Just the application of the principle of linearity. So here, we didn't bother to write it, we saved ourselves the work of writing it down. We had an inner product of a huge big linear combination with sine of mx. And now we're applying linearity, saying this is the linear combination, the equivalent linear combination of the individual inner products. So on this line, there was just one inner product operation. But on this line, there's a doubly infinite collection of inner product operations. But which inner products? Well, they're inner products between pairs of basis functions from the family F that we named in one of the previous exercises, right? And we emphasized there, we proved some parts, we left other parts to as exercises. So let's say we proved there that the family is orthogonal under the inner product. So everywhere we see here an inner product of one function, one basis function with a different basis function, it's going to have the value 0. So we've got a doubly infinite linear combination of stuff which is mostly 0. In fact, it's always 0 except for a single point. Here we've got the inner product of the constant with one of the sine functions, it's 0. They're different functions. Here we've got the inner product of one of the cosine functions with one of the sine functions, 0, because they're different functions. Here we've got an inner product of sine nx with sine mx. It's mostly 0 because almost all the time these are different functions. However, at one single point, they coincide. And by point, I mean one single value of the summation index. So there's one particular value of n for which these two functions are actually the same as one another. And that's when n takes on the value m. So you've got sine mx and sine mx in both positions. And in that case, the value of the inner product is pi. Okay? So everywhere it's 0. So you got 0 from this first one, plus a big sum of an times 0, plus a big sum of bn times 0 for every n not equal to m. But then there's one occasion where it's non-zero, and that's where n is equal to m. So it's bm times the inner product of sine with sine. And we just proved a second ago the inner product of sine with sine was pi. What's the justification there? The justification is by the orthogonality of the family F and the sine equals pi, when they're both the same functions, results as well. So from looking hideously complicated, it reduces to something quite simple. Just the parameter bm times pi. So in other words, just ignore the needless complication in the middle. What do we have from top to bottom? We've got bm pi equals the inner product of f with sine mx, which is the integral from minus pi to pi f of x sine m with x. And that gives us the coefficient formula. That bm is 1 over pi times this integral. So just dividing both sides by 5 by pi, this effectively is the given coefficient formula for bm. So we see it as a consequence of the existence of a Fourier series for f and the application of basically the orthogonality of the family of basic functions. And the fact that we're using an inner product, so we can apply linearity. Ooh, no, that's a rogue artifact. So that's an integral, so that should be dx. Yeah. The inner product is the integral of the product of the functions. So let's just button that. So again, just like the other ones, I'll set you another extra exercise. Some of these extra exercises I'm suggesting here, they're referred to in the end of in the sets of exercises in the notes. Provide a similar argument. I mean, you can kind of just basically see it really. Provide a similar argument in support of the other two other two coefficient formulae. Those were the ones for a naught equal to whatever it is and an equal to whatever it is. But they're effectively just exactly the same argument. But rather than having sine of mx here, you'd have cosine of mx or the constant function y. Okay, choosing the correct basis function to use. Okay, for once I've worked a little bit ahead of myself. So if you don't mind, I'm gonna finish on time for once, or maybe finish a minute or two ahead. But this evening we'll do our first Fourier series. So going from the function and obtaining the Fourier series. For two functions, for the square wave function, at least the square wave function and the identity function. F of x equals x. The square wave function is our this kind of function, square wave. So that's what we'll be working on, those examples, very calculation, example-based session this evening, okay?